So participants, I have dropped the drive link here. So I hope you all received it. Okay. So when you click on that link, you will find these three files. So this one is a zip file, the middle one, and the first thing is a video. If you want to, proceed with the video, you can go with it. But if you want to just follow along what I say, you can follow. So it will be a simpler case to run. You will not face many errors how you might have faced in the previous sessions. So the third one is a file based on which we prepared this case. So this is a report made by a case study at the FOSSEE. So you will learn what is a case study and everything in a couple of days at the last day of the workshop. Before that, you just know that this is a report based on which we made the case files. Okay, now you can download this file. So this is the one which I have shared in the chat box. For convenience, I have already downloaded only the zip file. So first, as usual, we will extract it. I'm going to use WinRAR and I'm going to extract it. So after you extract, you will get a folder named CHT case files _ FOSSEE. So you can copy it and paste it in a run directory. Okay, so I have my run directory open and I'm going to paste it here. Okay, so inside the folder which we just pasted, you will find another three subfolders, each named circle, square, and trapezoid. So this tutorial we are just going to run circle, and I will tell you how to run the square and trapezoid as well. So the procedure will be similar. So let's look at the circle folder first. Inside circle, as usual, you will be finding the 0.original, constant, system, the paraview file. But apart from that, you will also find two new files called all run and all clean. So you might have found this in the previous case files as well, but maybe you did not explore it. Inside the folder which we just copied and pasted, we have another three folders, namely circle, square, and trapezoid. So we are just going to look at circle. So I'll open circle, and inside that again you will be finding the default files 0.original, constant, system, the paraview file. But apart from that, you will also see all run and all clean files. So it does not have any extension as such. In the prior files which you have downloaded, you might have seen this, but we did not use it explicitly. So we will see what it actually says and why do we need these files. So we are going to run this case, the circle, square, and trapezoid, only using all run. So I will open all run file. You can either open it using Notepad or any text editor. I'm going to open it using Visual Studio Code because VS Code gives better visualization when we are looking at a C++ code. Okay, so this is the file which we have. Here, whatever is written followed by echo, you need not worry about that. This just says that we are going to print this command on the command prompt. You will understand it later when we run this file. So for now, just please follow along. You don't have to do it yourself. You can just watch what I'm saying. The first command will be cp -r 0.original 0. As you might recognize, this is to copy the 0.original file and paste it in a new name called 0. So because that is what OpenFOAM will understand, the 0 file. Next, we are running the block mesh command. So we are also logging it, whatever is happening in the block mesh. When we type block mesh in the command prompt, we will get a set of lines of codes or instructions which we will see, and we will notice that we are getting an end. And then we will confirm that block mesh has been made. But in this case, when we are running an all run file, we will not get commands on the command prompt. Instead, all the commands will be stored into log.blockmesh file. It is just a log file. Then next command will be topo set. So we will see what is topo set, and the information will be stored in log.toposet. Then the next command will be split mesh regions cell zones overwrite. We will also see what this command means when we run it. And the next command will be run application decompose par all regions dict. So we will also decompose this case to make it run faster. This is a bit big simulation, so it will take a lot of time. So it is better to decompose. Then we have the run parallel file, which will initiate the parallel simulation. Then we have the reconstruct par, just as we did in the previous decomposing cases. So again, we are creating a paraview file if we want. Okay, now we will first see how we can run the all run file after we understand these two commands. So the topo set is a command which we will first we will see what is block mesh. As we might know already, block mesh is a command which is calling the file block mesh dict, which makes a generic mesh. It creates a 3D mesh in a 3D space, and we have certain blocks. So that is what block mesh creates. Then we have the topo set. So what topo set does is that it will take the entire block mesh and mark certain regions with a different name or different patch. So we are setting a topology inside the 3D mesh which we have created. So that is what topo set allows us to do. We can play with topo set and create different regions within the mesh which we have created within block mesh. So this is just a convenient way of making a CAD geometry, a very simpler CAD geometry, without having to use any CAD software. So we are making a mesh and we are splitting it. So that is what topo set does. We will also look at the code. Then we are using split mesh regions cell zones override. So we will see why we are doing this command when we actually understand what is topo set. Then we are decomposing the case and then running it parallel. So now you can follow along and do the steps to run the simulation. So once it is initiated, we can see what are the case files which is being used to make the entire case. Okay, first I will open the command prompt. Make sure that you are in your run directory and you are using OpenFOAM 9. So that is essential.
Sir, did you elaborate the run parallel command?
No, we did not do that yet. I will do.
Okay.
One more question. This is not enclosed domain, right?
We will see the mesh. At the time, I will explain.
Okay.
So first we will see how to use the all run file. Now we have the file, that is the CHT case files underscore FOSSEE in our run directory. Now we will enter it. So you can enter it through the command cd space the file name. Inside that we will be entering into circle. Okay, so I hope you got till here. When you type ls, you should be able to find 0, all clean, all run, constant, and system file. Now we are going to initiate this all run file. Now please note, if you are on a Ubuntu machine, all you have to do is dot hash all run and enter. So this is all you have to do if you are on a Ubuntu machine. But if you are using WSL, then we need certain permissions from the system, and to make that we will be using bash space dot forward slash, and then we will type all run. So this is the command which we will be running if we are using through WSL. But if you are on a Ubuntu machine and using Ubuntu terminal directly, then you do not need the word bash. You can just start from dot forward slash and all run. Now I will initiate the case and you will see what happens to the command prompt. So when I hit enter, you'll see first the block mesh is running. Then the next command toposet will run, and then the split mesh regions will run. So as you can see, the toposet is run and the split mesh regions is running. So what it actually means, where is all the end case? So as I already explained, it is in the log file. So the log file is present in the run directory itself. You maybe have to refresh it. So once you refresh, you will see that we have log.blockmesh, log.toposet, log.splitmesh regions. We can open this file and see what actually happened with our case. So you can either open it with Notepad or VS Code, your wish. So after I open the blockmesh file, you can see that blockmesh ended properly. Okay, and similarly, we also have the case for toposet and split mesh regions. Now, when I go to the command prompt, I can see that each case is running one by one in a systematic manner in the same order which we defined in the all run file. Okay, now before this starts and stops running, please confirm that it is running without any error, the all run file. Okay, if it throws error, maybe you have to change the decompose file, which I'll say now. Yeah, that's what I said. There is no extension for all run file. It is just a script. Okay, that's good. It is running fine. Okay, now I will go into system and first explain you the decompose paradigm. So we are decomposing the case. Since we are running all parallel, I will explain the decompose file and then we will do it. So previously we were using methods called hierarchical, but in this case we are using a Scotch method. If at all your simulation throws an error, mostly it is because of this file. So it won't throw error in general, but if it is throwing an error, please change this number, the number of subdomains, to the value to which your the number of cores your PC has. So that is the number which you have to use. So that is the only probable error you might get if you are using OpenFOAM 9 properly. Okay. So I'll close this as of now. Now we will see what is there in the all run file actually. Okay. Now we copied the 0.original file to 0. Then we did the block mesh, and then we are running toposet, which is quite new, right? So we will see the toposet file first, and we will understand what is actually happening here. Okay. So now we are opening the toposet dict file. Here we can see that there are a set of commands. So let's understand what this command actually means. Now here we are seeing that name CO or C naught. Then there is type, which is called a cell set. Then we are defining a new action, and it is called as cylinder to cell. Okay, so there are other methods like box to cell, which you can find in the toposet file of the square case. So this is the circle case. So we are finding something called the cylinder to cell. We have the source info here. The P1 and P2 are 2 points in the 3D space. So this is X, Y, and Z direction. So, okay, this is the X, Y, and Z direction. On the x-axis, it is on the minus 0.1, and y-axis, it is 0. And the z-axis is varying with the 2 points. So minus 1 and 1. So you can imagine something like the point 1 is on the back face and point 2 is on the front face. We are defining a point with some radius, which will create a cylinder. We have 2 points with distance, and we are creating a radius. So that will create a cylinder-like structure. So that is what we are doing here, a cylinder to cell, and it is initially called as C naught. Now we are taking the set C naught and saving it in a name called heater 1. So that is going to act as the heater 1 for our case. So the case which we are doing is there will be a fluid domain, and it will have two solid bodies which will act as two heaters. So the two heaters will generate heat up to 1 second, and it will stop generating heat. And we are going to perform a conjugate heat transfer. Because of that, we will be giving an initial velocity in x direction. So once the simulation is over, I will explain the geometry and mesh. Then we have C2, or sorry, C1, which is the second point through which we are creating heater 2. Okay, now we have defined two cylinder like structures in the block mesh, and we have named it heater 1 and heater 2, but it is overlapping with our original mesh, right? So what we are going to do is that we are going to delete the overlapping cases. So we are again creating a new name called C2 with the same points, and we are deleting it from the original mesh. So that is what we are doing it here in the topo set. So we are first creating a new region, then deleting it, the overlapping areas. Then we are creating a new fluid. So whatever is remaining after deleting the two heater regions from the original block mesh, we are defining it that as fluid. So if you can imagine, we are having two heaters and a fluid domain. So that is all our mesh right now. That is all the uh, region that we have. So how to actually define all the regions here? How to create all run all clean? So you can take all any default file from any case, Then you can modify it based on the series of commands which you will be using. For this case, we are using copying the 0.original file, then we are doing block mesh, then we are doing topo set, then the split mesh regions. But if your case demands a different set of commands, then you just alter it. That's it. The syntax remains the same. Okay, so this is all about the topo set dict. Then the next command is split mesh regions as we ran it, but we do not have a file for that. So what we are actually going to do is we are splitting the mesh which we just created and put it in separate folders so that the solver can understand it. So what I actually mean here is when we go into circle folder, we will find these, the 0, constant and the system. Now when I go into the 0 folder, which is our initial boundary conditions, we can find 3 folders, namely fluid, heater 1 and heater 2. If you could recall, that is all that we created using the mesh and topo set. But after we create the topo set, each mesh has to go to its respective folder so that the solver understands the boundary conditions, right? So we are using the command split mesh regions. So what are we actually splitting? The cell zones, and we are overwriting the original polymesh folder. So that is what this command actually means. So we are running split mesh regions, what we are running, splitting the cell zones, and we are overwriting the polymesh. So that is all about split mesh regions. So after we run that, we will okay, now we have 3 regions, which is fluid, heater 1 and heater 2. So inside fluid, we will have set of boundary conditions, the velocity, temperature, pressure, and pressure minus hydrostatic pressure. So we have these 4 files for fluid region. When we go for heater region, we will have only pressure and temperature because we are not interested in giving a velocity to a solid body. Okay, so we are giving temperature and pressure alone. We will see what is the pressure and what is the temperature when we actually see the results. Similar to heater 1, heater 2 also has the same temperature and pressure. Then the constant folder. So this constant folder has again the fluid, heater 1 and heater 2. So whatever we did till now for other cases, we have only one region. So we will be defining all the case files like the boundary conditions or region properties, the thermophysical properties. It will all be a single file because it is only one region. But here we are having 3 regions. So we will be defining it in different files. So the next thing we have to do is define the turbulence properties and thermophysical properties. So this is a laminar case. So we have defined laminar and turbulence properties. And for thermophysical properties, it is very similar to what we saw before for other heat things. So here we are seeing the type H rho thermo, He rho thermo. Then the mixture is pure mixture. So here we are using a different fluid. We are not using air here. So it is water. Then we are defining a constant transport. Then the equation of state is a rho constant, which means the density will remain constant throughout. And for the species, we are defining the species which has molecular weight of 18. Equation of state, the density is 1000. The specific heat is 4181. So it is joule per kg Kelvin. And the heat of formation or enthalpy of formation is 0 because there is no chemical mixing here. Then we have defined the dynamic viscosity. If we could recall what we did in the nozzle case, we have defined the dynamic viscosity as 0 because it was an inviscid case. But now we are interested in viscosity as well. So we are defining the mu, and the Prandtl number is also chosen. So the same or the similar structure is also followed for heater 1 and heater 2. We can open it and see, but here we will have something called the FB models instead of the turbulence properties. There is no turbulence happening in a solid region, right? So we have a different file called FB models. We also had this in a previous tutorial. So I will open the FB models, but unlike what we did in the previous cases, we have a user defined code here. So it is okay if you do not understand this code as of now, but what we are actually doing is you just understand the physical meaning here. We are taking a heat source. So that is what this function says. The heater 1 and heater 2 are a heat source. So it is not just having a constant temperature. So it is generating heat for a certain time. So we are defining x less than 1. So what this actually means is up to time step 1, our heater will generate heat. So the value is 1E7. So it will generate heat, and after it reaches 1 second in the time step flow, the heater will stop generating heat and it will just maintain whatever is already there. So we will see visually through graph and also through contour plots. So this is a normal C++ code. If you do not understand, it is fine, but you can take this structure and modify the time up to which it is heating, or you can change the value for which it is generating heat. So this is all about FV models. It is okay if you do not understand it right now, but you can understand the structure. Okay, similar heat condition is given for heater 2 as well. Then we have the gravity, then gravity file. The polymesh is what we created, the original mesh file. Okay. The next main thing is the system. Inside system, again, we are going to have fluid heater 1 and heater 2 as we expect. Inside this, we will have the FV schemes and FV solution. Generally, we will just give one FV scheme and one FV solution here. So these two will be all, but here we have to define it for both. You can open and see what is there, and I have also explained it in the video. If you want, you can see them. Now we will see the block mesh dict and understand what the region we are actually working with. Here we have inlet patch, outlet patch, and we have fixed walls.
I think day before yesterday something I explained to you what is explicit and implicit. After today's session, I think you would have been able to understand better. So if you remember the code that we wrote today for scalar, right? The source that I added over there was minus k into the scalar itself, right? Minus k phi. The equation that we are solving is d phi by dt is equal to minus k times phi. So the source is also dependent upon itself, right? So it is not a explicit formulation, if you understand that, right? Like suppose if I write y in terms of x, y is equal to 2x, so y is written explicitly in terms of x. Okay, but if I can't write, if I write y plus x, the sum raised to power 2 is equal to 2x something, then I have not written it explicitly. You know? So that is what basically it means. So whenever you have a where is it written? So the source is divided into an explicit contribution and an implicit contribution. Implicit means it is written in terms of itself. Like in our case, like when we were solving, suppose say we were solving scalar today, we would have had to give the implicit contribution as say maybe whatever is the value of k, right? So if I give the value of implicit over here as 2, it will take it to be, say, in our case today, 2 phi. The source would be 2 phi. So it will not only take implicit value as 2, but also multiply it to itself. So that is your implicit contribution. But explicitly, whatever value you take will be added directly. So that is your source written explicitly and implicitly. So the same thing can be, you can just go for what you can say, the way I have defined the source, because I've already defined it in the source code, so I don't have to write it explicit and implicit. But here they don't define that way in the source code. They will just write FE models. But when we specify this explicit and implicit contribution, it will take care of itself. That means the source value is dependent upon itself. I think I am clear. Yeah.
Like I want to understand this part like a little more. So this type coded means like it is taking the source through the code, right?
Yes.
And what does this heat injection means? Like it's so heat.
Okay. Yeah, that is the name that he is given. Okay, that is just a name that he is given. I don't know whether it is specific to this, but what this code basically means is, I think what Harish has already explained is, you have given one, you have created one scalar called as amplitude. Okay. That is the value that you are going to be giving, right? Now, if your time x is the current time over there, okay, it is because it is FE models, it will be able to, what you can say, it this will be read every time. Because if you look at the source code, it will be equal to FE models. So every time it comes to this, it will read whatever is the current time, right? If current time is less than 1, it will add power, right?
Okay.
This power amplitude. It will add this source term explicitly, right? That means
Okay.
this, whatever is the value, it will go and add it over there. Else, if once that time is over, right, after 1 second, the heat source addition will return 0. That means you're 0. So that means you're adding heat only for 1 second. It is like switching on the heater for 1 second and then turning it off. So if you want to see that, so that is the explicit part. I think that Harish has already covered. What I wanted to say is the difference between explicit and implicit, that you could have understood by what the way I have written the source code today. So the way I had written the source code for the scalar in the morning session, that was written in the implicit formulation, because the what you can say, the equation for scalar was dependent on the scalar quantity itself.
Okay.
So
So,
but
and also this small e, what does that mean? Like,
so he has written over this. If you scroll up, Harish, can you scroll up? Oh, it is not. It is the energy. I think it is the internal energy, because in the models, if you see the what is that, thermophysical properties? Can you just see the He has written
Yes, okay.
E constant. So E constant. Okay, so you are solving this E constant model.
okay, where is
So
the T constant?
So it's no, sir.
Where is that?
We
No,
don't-
E is your sensible enthalpy. So your
Right.
whether it is
Okay.
for the same one or
Yes, same one, sir.
yeah, okay. And okay, so it will solve the energy equation either. See, as far as what I understand, either it will solve for the E equation or the H equation. In fluid, it will solve for enthalpy. In solids, it will solve for internal energy. Okay, so it will solve for E in solids. Okay. So whenever you want to work in fluids, it will solve for H. This is what I have understood from this. Okay, between the two.
And this-
Previously, I think they had the same equation for previous versions of OpenFOAM, but for these versions of OpenFOAM, they have shifted to E.
Okay, okay. And this X,
And the other X is the way this code gives you the current time. I know that X shouldn't have been the time, but that is how this code gives. So this is also available in their source code. If you like yesterday, I showed you, right? If you see, whenever you read X, X is given as the what you can say, current time in this format. So X does not seem like time, but that's why the comment Harish has given that comment over there, right? X is the current time. And one more other important thing is this volume mode that he has given. It is specific, absolute. Okay, that. So if you are adding, so I think yesterday we discussed. If I want to add a total of 100 watts, then I will write it absolute. But if I give the value in terms of volumetric value, like watt per meter cube, then this will be specific.
Okay, understand. Thank you.
Yeah.
Okay, we have we were seeing the block mesh. We have the inlet outlet. We have fixer walls, which is top and bottom. Then we have front and back. So the front and back is termed as empty, so that we are getting a 2D case. Now we will just visualize the mesh so that we will understand the case better. So I think the simulation is over. Yes. So after the simulation is over, you should be able to find case files 1 to 10. So these are your 10 time steps, 10 flow seconds actually, flow time. So we will see that. Now we can open the paraview file. When you initially load the paraview file, it will look something like this. Maybe the colors are different, but mostly it will look something like this. This is the what it actually does is paraview takes the entire geometry and defines different region in different color. So that is what it actually is doing. So it is taking the VTK blocks, which is a type of mesh which OpenFOAM understands, and it is coloring by different colors. So you can understand that we have 3 mesh regions. The white is heater 1, the blue is heater 2, the red is heater, the fluid, which is actually flowing. Now we are at the first time step. I will change it to velocity. We can see that there is a flow which is happening around the heaters. Now I will change it to temperature. Then we will understand what actually is happening here. You can see the contours here. So we are getting up to a certain, the inlet velocity. The inlet fluid has a temperature of about 300 kelvins. So, and there is the heat source which is heating the fluid. So as the fluid flows over these solid bodies, it is actually generating the heat, and when there is a forced convection, it is conjugating some heat. So it is only up to the first time step. So since we have saved the file only up to the first time step, we cannot see what happens in between 0 and 1. We will visualize that through graph. So till first time step, we are generating some heat through the heater, which you can see here. It is slightly above 302.5 and below 303 kelvins. So that is what is happening till the first time step. But when we go to the last time step, which is the 10th second, you can see that the heater's heat has reduced. So I will rescale it to the visible range. Now you can see that the maximum is less than what the heater was initially there after the first time step. So we will visualize more using the graph. So what I actually mean here is, after we introduce the flow velocity and we stop the heat generation through heater, the temperature decreases as we would expect. So that is what is happening here. Now we have certain functions which is written in control dict, which we will use to visualize the heat generation and drop later. But before that, we will also see that we have a velocity flow from left to right, which is on the positive x direction. And if you want, you can also visualize the pressure minus hydrostatic pressure. And if we go to rho, we will see that it is uniform 1000. So if you could remember, we defined it as rho constant file in the thermophysical properties here. So we have a rho constant type. So the density will be kept constant. It will not act compressibly. The heating effect will not have an effect on the density of the fluid. So that is what we are doing here. Now we will see what are the functions which we have written. The functions which we wrote will be inside the system folder. Inside that, the functions are called cell max heater T, cell max heater T2. Then we have volume average heater T and volume average heater T2. So the cell max function, it will take the cells in heater 1, the file in cell max heater T. So what it actually does is, we are defining and giving it a region to work on. So the region is heater 1, the left one. So it is taking the heater 1, and the field which we are interested in is T, which is temperature, and it is calculating the maximum value there. So it takes the entire region and see what is the maximum temperature achieved in that region. Probably it will be uniform, but because we have given a weighted average, so it will be sort of uniform, but it will not be. So we are using this maximum function so as to calculate what is the maximum temperature available within the cell range. So a similar code is written in cell max heater T2 as well, but there the region will be heater 2 instead of heater 1. So that is about this function. And if we go to the volume average heater T, so this file will take the volumetric average of the heat, the field T. It is what we have defined. So it will take the volumetric average of temperature, and it will give the data to the post-processing file, the .dat file, which we will be plotting, which we will be using to plot the graph. So it will take the value, store it for each time step which we will be running, and we will be having a .dat file which we can post-process to plot the graph. So this is a normal case which will be, or a normal function which we can use. It does not take in any numerical inputs other than what field which we want to calculate. So this is all about volumetric average too. Okay, we have the control dict where we can see there is application. So CHT multi-region foam is the solver which we will be using. So conjugate heat transfer multi-region foam. Then we have delta T, which is 10 power minus 3. Then right interval is 1. So that is why we are getting the files for every 1 time flow second. So which is 1 second, 2 second till the 10 second. Then we have defined the 4 functions which are cell max heater T, then volume average heater T. This is for heater 1, and these 2 for the heater 2. So that is all about control dict as well. Okay. The next command which we used was run application decompose par, then all regions dict. So we have 3 regions: fluid, heater 1 and heater 2. We have to decompose all the regions. So that is why we are running decompose par. So the run application just means we are running a sort of application through the command. Instead of running just command which is opposite here. So this is a normal command. This one is a run application command which gives a command directly to the root. So decomposing is like accessing your CPU directly. So we will be using run application. This is a syntax which we are using. Then we have the decompose pair, then all regions, then dict. So this is a normal syntax which we have to follow in order to decompose a multi-region type of case. Then we have to run it parallelly. So if you could recall, we were writing a command like mpi run number of processors, so np8. Then we will define the number of processor. Then we will run the case files. So it will run in parallel. Instead of writing all of those commands, what we can do is we can type in run parallel, and we will give a command called $get application. So what this get application will do is it will go to your control dict. Inside your control dict, you can find you have a keyword called application. Near that, we will have CHT multi-region form for this type. So this simulation is running based on CHT multi-region form. So what this all-run file will do is it will find out what is the application that we are using, and it will run that application in parallel. So it will automatically type the mpi run number of processor which was used in decompose pair. So it will do everything automatically. And after this simulation is over, it will also run the reconstruct par command in parallel. Sorry, in application, it will run in series. So run parallel is to run a command in parallel, and run application is a command to run things in series. So we are reconstructing everything in a series processor, which means it takes in only one core from your CPU. And we are reconstructing all regions. Since we decomposed all regions, we have to reconstruct all regions as well. So once it is reconstructed, before it gets reconstructed, we will have files like processor 0 to 7, inside which we will get the time steps for each decomposing. So the decomposing is like it will split the mesh within the processors and it will calculate simultaneously. So this is not something which we can visualize directly. So we have to reconstruct, and we have the entire case with the total mesh. So 1 to 10, we have the time steps. Then as usual, we will find the dynamic code folder because we are using a user defined code in FV models. Apart from that, we will also have post processing. So this post processing folder will have two other folders, namely heater 1 and heater 2, because we have given the function to calculate maximum temperature and volumetric average temperature in heater 1 and heater 2. So when we go inside this, we will find both the things. So cell max values and volumetric average values. Now we will try to plot these. So the method to plot these is to go before that, is simulation over for everyone? It should be over by now. So if someone can confirm, I will start with plotting graph. Okay, so the process to plot the graph is we will be using a utility function called home monitor. Then we have to define the path to the file which we will be taking to plot the graph. So our path will be from circle. We have to navigate to the .dat file. So it will be post processing. Let's say that we have two heaters. So heater 1 is what we will be plotting first. Inside that heater, we can find two folders, namely cell max heater T and volume average heater T. So first we will plot cell max heater T. Say that we have 0 folder again, then we have volumetric field value dot. So I will hit enter and the GNU plot will pop up. As you can see, till the first time flow or the flow time, we will be seeing a heat generation or heat increase in heater 1. After 1 second, the heat will start to drop. So initially the heater is at 300 Kelvin. Then we are heating it slightly more, then that it reaches 302.75, close to something like that. Then it starts to drop because of the conjugate heat transfer, because the inlet fluid has a temperature of 300 Kelvin. So it will try to bring down the temperature. So that is what we are observing here. I hope this is clear. You can also find a similar graph in the report which we had shared. So that is the original case file. So there is a validation as well there in that original report. So we are seeing an increase and then drop because of the conjugate heat transfer. Now we can close this graph. Then we will plot the other graph as well. So the other folder is volumetric average. Okay, we can observe the similar kind of graph here, but we can also observe that it is not reaching up to 302.75. It is slightly below because it is taking average, and so that is why we are seeing this, because there is a conjugate heat transfer even when there is heat. So even when the heater is heating up, there is some kind of heat transfer which is happening with the fluid, which is trying to bring down the temperature of the heater. So then it starts to drop and the volumetric average drops as well. So that is about plotting these graphs. If you want to do it for heater 2, you can do it just by changing the path. Now shows unable to plot. So can you please type the command which you actually used?
I typed the same command, but last time is also showed a GNU plot is unable to plot.
Okay, so what you
About
can
it
do is,
case the GNU plot.
yeah, okay, then in that case, if GNU plot doesn't work, you can navigate manually to this area. You can open this file, or you can import this file into Python or Excel, then you can plot it. Is that okay?
Okay.
Yes, okay. Case 1, if file 0 to 10 did not generate in the processor file, maybe you can try changing the number of cores in decompose product file. Maybe. Else, your command prompt was interrupted probably. Okay, regarding what we did for changing the temperature here, we can see that first we are defining a heat source. So the heat source is taken as semi-implicit source, as John sir explained. So this is our explicit method of defining heat. So we are using semi-implicit source. So this is a type. There are other types too. If you want to use any other type, you can follow syntax of that thing. Then for volumetric mode, we are taking specific. So there are two types, which is absolute and specific. So we are taking specific. So absolute, as sir said, it is like defining temperature directly. But for specific, it means per kg or per volume of area, for volume of the heater, we are defining a temperature. So that is difference. So otherwise it is same. So it is just like defining a temperature. Then selection mode is also, all this means we are selecting all the cell zones within that area. So within heater 1, we are selecting all the cell zones. Okay, then the sources. So the sources are of two types. So either you can give heat source or energy source. So here we have chosen the energy type. So then we are giving the explicit. So explicit has the total weightage and implicit has zero weightage. So that is what implicit 0 here means. Then we are using the type coded. So if we want to do a different type of explicit way of giving heat, for example, if you just want to keep on increasing till the time step ends, there is a way to do that. It is also a type of heat injection, but there is no stopping of heat after we start the simulation. So it just keeps on increasing for every time step. So we do not want that in this case. So we are giving type coded. So wherever you want to give user defined function, you can give the type coded. The name of the code, it is just like a placeholder. So the name of the code which we are using here is called heat injection, because we are giving in a heat. So we chose that. Then the followed by the code. So the code is like, there is a constant scalar, like how John sir explained in the morning. We have power amplitude, which is of 10e7. Then we are defining the time up to which we have to give the heat. So this is a if else function. normal if else function which we will be seeing in coding. So when the time step, in this case it is x, so when the run time is less than 1, we will give the power amplitude of 1e7 to the heater, so it will increase by 1e7. But if the time has crossed 1 second, then it will fail the if condition and it will go to return 0 and there will be no heat generation. So that is all that we are doing here. First, we will be seeing whether the time step is less than 1. If it is yes, the power amplitude will be increasing, the heat is increasing. If the time step is more than 1 or equal to 1, then there is no heat generation, that is, the heat is given as 0. So then the explicit is also 0 and implicit also 0. If anyone is still trying to run, I will just clear this command prompt and try to type the case name. So that is the command you have to run if you are on a WSL mission.
Yeah, so for me, the case files are not getting generated. Is it because my laptop has 6 processors, but like in the decompose part it is 8. Is it because of that? Like I'm rerunning it again, it is taking time. I don't know, maybe someone else is also facing the same problem.
Is your computer having 8 subdomain, 8 cores or less?
6 cores, yeah.
Yeah, did you try to change the decompose file to 6?
Yeah, I changed it now and running it. It should generate the case files now.
Yeah, but before that we should have cleaned the file because it would have
Yeah, that I
generated
have done.
something.
Yeah, I have done the form clean place and then rerun it.
Yes, okay.
But it should take as many, like, is it dependent because it has more than, like, though it is 6 cores, I think it will have 12 virtual cores, right? That does that.
Okay, since we are using a machine that actually takes things from CPU, unlike commercial solvers like ANSYS, there we will be giving the logical cores instead of physical cores. But MPI, which is operated by OpenFOAM, it does not take all the threads, which the logical cores, which is also called as threads. So OpenFOAM cannot access the threads. It only takes the power of physical cores.
Okay.
So we have to define that.
Okay. Okay. Thank you.
Okay, if anyone has already run the files and have post-processed, tried to plot the graph, we can run bash space dot / all clean instead of all run. What this file will do is it will remove all the folders, all the files which was generated during the simulation, and it will give you the default case which you had when you downloaded. So we can also customize this all clean file. There are other methods which you might have learned in the previous tutorials, or else you can manually clean everything by typing this. There are many methods to do an all clean things. So we will see what this actually means. So first, the foam list times rm. This command will clean all the time steps which was generated. In our case, it is 1 to 10. So this command, the foam list times rm, so rm stands for remove. It will remove all the files, all the time steps which was generated. In our case, it is 1 to 10. Similarly, rm minus r. So minus r means removing a folder. So you might recall the cp -r. So it is also saying there is a folder, we are copying a folder. So whenever we are copying or removing a folder, we have to use the -r. You are removing the dynamic code, we are removing the post-processing folder, then we are also clearing everything, all the files or folders which starts with the name log. So in our case, we are having log.blockmesh, log.toposet, then log.cht multi-region form. We are having a lot of log files. So we are removing everything in this case. So whatever starts with log, then the star means autofill. So we will be removing everything. Then we are also removing the 0 file because we already have 0.original. Then this command, the find dot type D. So this is a Linux syntax. It's not an open form syntax. So we can use this to search for any folder or file which has a name polymesh within all the subdirectories. We may be inside the case file, then we will have subfolders like 0, constant, and system, and under each subfolders we have fluid, heater 1, heater 2, within which we are having polymesh. So there is a polymesh folder in a lot of places. We can't just navigate to every place and remove the polymesh. So we will use this function. So D is for folders. So in this case, we are finding all the folder named polymesh, and we are executing a command named remove of the folder. So this command will remove all the polymesh folder. Then we have this command which is find type F. So F means file, and we are removing all the files named cell to region. So cell to region is the file which actually defines your mesh to a specific region like fluid or heater 1 or heater 2. So we are just removing all the files which was generated during the simulation. Before I run the all clean file, I think some people are having trouble in visualizing. So first let's run the paraview file again and see how to visualize velocity. First I will open the paraview file. Then we will click on apply. So any changes or any loading of file will happen only if you click on apply. It will take a bit of time. So after that you will see something like this. Three colors, different colors probably for you, but there will be three colors. The green one is, in this case, is heater 1, blue is heater 2, and red is the fluid region. If you want to see the specific flow parameter, you can go here, choose VTK block colors. So we are just seeing the mesh in different colors. Instead of that, you have to choose velocity or pressure or the gauge pressure, then the density or temperature. You might wonder, we also have these things. So what is the difference? This is point data. So it will produce smooth contours when you choose point data. Let us see an example. So when I choose velocity, it will be much easier to visualize. We have this smooth contour. Just in case, if you do not see similar colors, it is maybe because of a different color map. What you can do is go to the left panel, click on edit. You will get this right panel. Click on select a color map, and you can choose turbo, which I am using right now. But if you want to choose a different color map, then it's up to you. After we get this thing, we are seeing a smooth contour, right? So it is because we have chosen point data. But if we choose cell data, it might not be as clear as we might expect. So maybe it is dropping, the frame is dropping for you through Zoom Meet, but you can see here we are getting these things, right? So at a very small level, it is all just small blocks. But when we are using cell data, it will all be smoothed out. You can see in this region. So this is cell data, and this is the, sorry, that is point data, and this is cell data. So cell data will take values only of each cell and it will display to you, whereas point data will take values at points and it smooths out. So point data is, it's good visually in many cases, so we are using that. So I think it is okay with cleaning the case. So now I will run the all clean command. So it is for WSL users, it will be bash space dot / all clean, and we can hit enter to clean everything. So just to make sure, does anyone have any other doubts in paraview? No, maybe just once more I will demonstrate. Okay, Siva, are you running through direct parafoam command or using the paraview file? You're opening using para.foam, right? Okay, then technically it should be working. Should not throw any errors. Let's see what is the error. error reading file. So I think it is having error reading file, meaning maybe you run the file 3 times without cleaning or with cleaning. So that is also matters. Utsav, I do not see the files after it is reconstructed. Did you run reconstruct par? You have all the processors, but I don't see reconstruct par. So only if you run reconstruct par all regions, I don't see if you have reconstructed. Okay, Siva, I will try to maybe let you present and we will see, because I don't know what is the problem without seeing the entire error. So this is the final velocity output and this is the final temperature output which you will be getting. Okay, now I will run all clean. So for WSL users, it is bash space dot forward slash all clean. If you are using Ubuntu, you don't have to type bash. It is just dot forward slash all clean. Then hit enter. It will throw some errors. Do not mind it. Now, how you can verify is you just refresh the folder, then you will see. But after you run this all clean file, if you see processor 0 to 7, then you might get the clarity from the video. You have to type another command to clean it. Siva, when you open the paraview file, on the left it will ask skip 0 time. If you have already checked it, check out, or if you deselected that, it should not be. You have to skip the 0 time file, because at the 0 time the paraview will try to load your temperature and velocity files. Yeah, it should be ticked in, like skip 0 time should be ticked in by default. You should not change anything, because the paraview is trying to load your 0 file, but 0 file does not have any specific simulation values like for temperature or velocity. It is just boundary file, right? So if there is no tick near skip 0 time, please make a tick. Only then it will load properly. I think that is the error. Okay. Now there is a small thing that we made intentionally in the okay, good, Siva. When you run the all clean, you will still see processes 0 to 7. So this is made so that you can always reconstruct and see what is there in the processor 7. So just to reduce the space, sometimes you can delete the processor files alone or delete the reconstruct alone. There is one more thing which I want to demonstrate. Now I have cleared all the time step files, but no, I can still load the uh, paraview file without having to reconstruct it by choosing one small thing. I can click on decompose and load the files without having to reconstruct. If someone did not reconstruct and trying to load it, you can do something like you can click on paraview file, and instead of selecting the reconstructed case, you can select decomposed case and click on apply. Then it will still load without having to reconstruct, I am saying. So that is one more method. If you want to remove all the processor files too, then you can type rm -r rock star. So this command will remove all the processor files too. So rm is remove, -r is folders, then any file which starts with the 4 letters PROC, which is processor 0 to 7 in our case. So I'll refresh it, and we have the files, the default files which we downloaded initially.
Sir, in the constant directory, we have a file name G. The values are set to 0. So can you please tell what is the significance of that G file and where will it be useful?
Yes, the G file is gravity. Here we have defined 0, 0, 0 in all axes. But if you want to work with gravity, then you can change the y-axis to minus 9.81. So it is on the downwards. So if anyone is facing any issue, please tell me before I move to trapezoid case.
Yeah, just to add to what Rinkesh was asking about the G file. So in the current case, you see that the G file has not been included by Harish because it is forced convection and natural convection's contribution will be minimal, right? But in our case, when we simulated natural convection yesterday, so that time we had selected gravity because gravity was what was driving the flow. So depends on what is more dominant. So whether you want to give G or no. In the present case, even if we provide a G, the results will not change much because the flow is set by the inlet velocity. Only if the flow velocities are very low, then you have to see the contribution from both natural and forced convection.
Okay, now we will see trapezoid case. The square is similar. You can just open it and run the all run file. But you can do the same in trapezoid as well, but there is a small change. Here you can't find the topo set file. So as you could remember, the topo set was used to separate the regions from the block mesh and make the two cylindrical heaters. In square case, you will be having a topo set where cylinder to cell is not used and box to cell is used, and we have created two heaters through that. But in trapezoid case, we do not have the topo set. So how are we creating the the heaters? So what we are doing is we are making it in the block mesh itself. So here we are defining a lot of points and we are creating the heaters through block mesh itself. So if you want to understand this code, you can draw everything manually and visualize, or you can use ParaView to visualize. Now I will explain how it actually works. First, I will enter into the trapezoid folder and I will just run block mesh alone. Okay, now I have run the block mesh alone for visualization purpose. I will open the ParaView file. See, now we have the fixed walls, then we have inlet, outlet, and front and back regions, right? We have only these in the block mesh, actually. Now, if you see the all run file, we have the split mesh regions as usual. Yes, okay. Now we will run that and see how this actually changes. Before that, let's see what is there inside split mesh regions. So there is no file, so we will run it and we will see what actually happens. Okay, as we saw, initially the block mesh was something like this. We did not have any trapezoids here as we might expect. Now we will see what happens after we run the split mesh regions. Now I have refreshed the case. So it will take some time. So whenever you want to refresh a case, you can hit refresh here after you press parafoam or the foam file. Then you can hit refresh and it will refresh once. It will read the files all again. So that's what refreshing is. Now, yes, now we can see that we have two trapezoids. Yeah, so these are the two solids which we are using. And here on the left panel, you can see each split region. So everything is split. And here we can also see that we have heater 1, heater 2. So these are all interfaces. We will just see. Okay, I have selected internal mesh. Okay, so this is the interface which is there between heater and the fluid. So we have defined it as fluid to heater 1 and fluid to heater 2. And if you want to just view all the internal mesh, you can select internal mesh and see it, which I'm going to do now. Okay. By any chance, if you do not see multiple colors, maybe you are on solid color or VTK composite index, then it might look different. What you have to choose is VTK block colors to visualize each blocks in different colors instead of having a gradient. Yes, I can show you the split mesh command. It is split mesh regions space -cell zones -overwrite. You have the all run file. It is there already in all run file. You can copy paste in your command prompt. So the purpose of all run file is whenever someone sends you a open form case, they have to include all run and all clean file, so that when you just look at the case file, you will know what are the series of commands you have to run. Maybe you miss it. For example, the reason why we took the trapezoid case is that when we actually see here, we do not find a topo set dict. So we might not guess that we have to run split mesh regions. So by experience, we will know that we have to run a split mesh region command. But what if the author themselves say it in the first place? So you need not have to worry about it, right? So that is why we are having all run files. So either you can just get a case and run it immediately with the automation, like the series of commands, or you can know what are the commands which goes in to simulate the case. So that is the purpose of having all run case. And the purpose of all clean is we should not be removing some essential files unknowingly. So having an all clean case as a original file will be beneficial, so that we will not essentially delete any essential files. So it is plus to have all run on clean files whenever you send an open form case to someone. Okay, if you want to run the trapezoid case, you can. But before that, I will show you the topo set dict for square. Okay, if you could recall, we used cylinder to cell in case of circle case, where the heater was a circular geometry. Here we are using box to cell. So you can find a function called box. There you will find two inputs, two coordinate points. So what it actually means is that this is the left minimum point. So imagine a cube, okay, a cube or a cuboid. So it has a major diagonal which connects the lower point of the front face and the upper point of the back face. Maybe I'll show you here. So just for visualization purpose, if you assume that the point 1 is here, the front face lower point, the point 2 is on the back face upper point. So it creates a diagonal across the entire region. So that is what these 2 points are. So we are creating point 1 and point 2. With that, it can create a region, a cuboidal region. So we are creating a box to cell here, and we are setting that to heater 1. Again, we are creating a box to cell region. Then we are setting it to heater 2. Then what we do is we will subtract those region from the original block mesh. So that is what we are doing here. We are deleting those two heaters from the original cell. Then whatever remains we are setting it to fluid. So you can, whenever you are running an open form case, you need not write everything from scratch. So for example, if you are running a new case, maybe with a triangular heaters, what you have to do is, or a bigger box maybe, what you can do is you can just copy this case, you can paste it in your directory, change all the parameters which you want. Maybe you want a one box bigger, the other box smaller. You can change it on your own, visualize it in paraview before you run the mesh. Then if you want each heater to have a different heating, or any type of changes which you want to do to the case, maybe you want a higher velocity, inlet velocity, you can do anything by copying a case. So that is what OpenFOAM allows you to do. You need not do everything from scratch. So if anyone is still facing any problem, please tell us. We can sort it out. Maybe you can try running the trapezoid case through all run file or square case through all run file and see if you face any errors. Okay, Rahul Sharma has a doubt. So whenever you are coming across any solver, if it rings bell, like if it is known to you, then it is fine. But if you do not know what that solver actually is, then what you can do is you can go to the tutorials folder. Let me show you. So now whenever you are in your run directory, you will see something called tutorials. So these are the default files which OpenFOAM gives you to understand the structure in many times. So you can go into tutorials and you will find all types of simulations there. So these are some default files which you can take and edit. When I was saying that whenever we are using OpenFOAM, we will take the existing files and we will edit to what are the case we are doing. So this is one such place where you can take the tutorials. So the interFOAM, as you said, it is a multi-phase solver. So after you go to tutorials, inside that we have multi-phase, and inside that you can find interFOAM. Okay, so in interFOAM, again we have three main things. So we have a laminar case, we have large eddy simulation case, so that is one type turbulence. Then we have RAS, Reynolds averaged simulation types. So maybe if you just go into laminar, you will find a lot of case here, like dam break, which you will be learning tomorrow, I hope. So you will be learning bubble and dam break tomorrow. So you can explore the interFOAM through this. You can take this folder and you will find all run files. So you can see what are the commands essential for running such cases. So maybe I think you will learn dam break and bubble rise tomorrow. Then we also have large eddy simulations where you can see the nozzle flow in 2D. You can try to run it. And even if you take RAS models, you'll find a lot of cases. So everything already has a pre-built block mesh or type of simulation which you can do. Some things like propeller will include advanced meshing like a snappy hex mesh, which is not covered in this tutorial. So in this workshop as well. So you can try to read how to run the all run file. You will also find something called all mesh file when you come across some tutorials. So it is all the same structure. Whenever you are having any problem, you can go to the documentation, which is like openfoam.org or openfoam.com. So you can go there, or there are other forums like cfdonline.com. Then you can go there and ask doubts, or you can run the existing read the existing documents itself. So the one which you are talking about, interFOAM, yeah, it is a multi-phase solver, and whatever the case is, you can try to put it in your run directory and try to run it. That's it. How much difference in time we will find if we run LES instead of RAS for the same problem? So it all depends on the problem actually. So we can't generalize, in my opinion. I don't know. It might change with case, as far as I have seen. So if it solves for temperature, then yeah, you can do it. I think, let me check which solver has temperature as well in multi-phase. So whenever you want to find if we can include temperature or not, you can go to the existing case files and see if there is a T file. So that is something you can do quickly to find whether the solver can solve for temperature or not. But there is a folder called um, heat transfer itself inside the tutorials, where you can find all the simulations related to heat transfer. So like buoyant simple foam is there, buoyant pimple foam, which is a transient solver, is there, and we also have CHT multi-region foam, which we just used. So if it is a modified solver, like how you saw in the morning, you might be seeing a WMake. WMake file will be there. Once you run the WMake file, that solver, the new name of the interform, maybe a modified solver, it will get stored. Then you can run it using that command. So similar to what John sir explained in the morning.
Sir, can you explain this PRGH file and how it is different from P file?
Yes, let me quickly tell you that as well. Now, whenever you have something, a doubt related to any case file, you can type that. For example, in our case, we have doubt in PRGH file. So we just type that and we will get the official documentation. This is how we check the documentation. So when we go there, they will mostly have cleared it explicitly with mathematics and everything. So here you can see we have the hydrostatic pressure, which is RGH, which is rho GH, which we generally use, which they have mentioned here. So the file which we are using is an alternative pressure. So it removes all the hydrostatic pressure effects. So you can see this is a modified pressure, so the P dash. So instead of writing P dash, we have to write P minus rho GH, but the case structure, it cannot understand hyphens, so we are using underscore. So it is pressure minus rho GH, which is the hydrostatic effects. So we are removing the hydrostatic effects from the original pressure. So this is something which we study with the gauge pressures. That's the thing.
So, but in our case, we have set G to 0. So, does it have any effect here? PRGH, if it will not
Yes,
be
I
there, then
thought of
also.
doing that in visualization. Yeah. So this is just a case structure which we have to follow. But when we define both of these things, as you notice, the G is 0. After we post process everything in ParaView, the P and P underscore RGH, both the results will look similar. If you run the simulation which we gave you, yeah, it does look similar. So if you have any doubts related to OpenFOAM, then this is one forum, very useful forum. This is called a CFD Online. You can go there, create an account. There are a lot of problems which you are facing is probably faced by someone else even very long back, even something around 2009. Okay, so OpenFOAM is there for a very long time. So probably someone has already had a problem which you are having right now. So mostly if you ask the question properly in your Google, you might find an answer in cfdonline.com right away. So it is just a forum. You will find a lot of threads inside. As you read, you will find a lot of answers. You can try it out.
Yeah, Harish, just to add one more thing, people are asking about temperature dependent properties. So can you just share that thermophysical properties model once, Harish?
Yes, sir.
Yeah. So I have also shared the link, but just to maybe tell the people. So thermophysical models. Yeah, if you open this.
Of heater or fluid?
Yeah, anything. So if you see over here, the transport properties, people are use this constant. So instead of constant, you see the documentation that I have given to you in the link. There are different ways, like you can specify whether it is constant, whether it is a polynomial. That means you have to give a polynomial function with t. So you have to first find out how it is varying with t, find out the relation, like say a0 into t raised to power 1, something like that, plus a1 into t raised to power 2. So you can find those coefficients, and you can vary the properties based on temperature as well. Like similar, like in one case, I think for natural convection, we had used Boussinesq. So in that, density was being calculated from reference density beta and t. So there it was temperature dependent, right? So similarly, and when we write, say, ideal gas assumption for density, right? Here, equation of state instead of rho constant, if you give an ideal gas, then it will calculate the, what you can say, the property, the density based on temperature. So all those things are possible. I have sent one link, I think that is for V11. Mostly it should work for V9 also. So there are many ways in which you can add temperature dependent properties. So you all can go through that, and maybe you can explore, change those things and see how the result changes. Yeah, I think that's it. Okay, thank you.